Hi there, welcome to part 7 of Let's Design a Drug. Today we're going to be talking about the filtering process, as we've been talking about for a few videos now. Last time we ran a QikProp job and a Glide XP job, and I kind of want to show you guys what that looks like. So if we have our workspace open, we can go to our project table, and our project table has 100,000 ligands that we docked from tranche 1. As we talked about, I'm going to pull this all the way over my other monitor so we can just focus on visually what's happening. So what I'm going to do is go all the way down to the bottom of my entry list. I'm going to display the receptor. And what that looks like is I have basically just double-clicked the receptor in the entry box, and that keeps it on the screen. And then, for example, if I wanted to display a ligand bound to the orthosteric binding site, I could go all the way up, and it would show me that this entry okay. This entry is actually our top hit right now for a ligand that binds to cannabinoid type 2 receptor, and it, structurally, we said before, it should have this sort of carbonyl group, ketone sort of functional group, and that's because that should hydrogen bond to serine 285, as does our co-crystallized ligand that we talked about. And lo and behold, it does. That's good. That's good stuff. Let's go to residue for selection. Serine 285, perfect. So we have that hydrogen bond. We also have another hydrogen bond to, what is that, threonine? Threonine 114, interestingly enough. There's something kind of cool I want to show you guys. We talked about, like in one of the first videos, that a ligand recognizes a receptor by its three-dimensional shape and also electrostatic charges. It doesn't care that it's a carbon, hydrogen, nitrogen, or oxygen. There's kind of a cool thing, there's a cool terminology in pharmacology called the Pharmacophore model, and it basically refers to the shape that you should build your drug so it should bind to the binding site in a nice fitting manner. And here's what I mean. If I take a bunch of ligands and I select a bunch of them, I'm going to do this by holding control. I'll kind of show you on here. I'm going to scroll down maybe to 100, hold shift, and click. It'll ask me, do I want to include 95 entries, degrade performance, go to continue. It will make the computer just a little bit laggy. It will make my computer a little bit laggy, I should say. Here's the cool thing about sort of a pharmacophore model. This looks like an absolute mess. But actually, these are some of the highest, these are some of the best hits, and I've overlaid them all on the binding site. And it kind of illustrates an interesting story. Theoretically, if we built a molecule with the following interactions, we'd have a very tight binding, high affinity agonist. And what I mean is, for example, this amino acid right here is tryptophan, and our pharmacophore model would tell us that, pi-pi stacking here would be really favorable for a good interaction here for a tight binding ligand. Right over here, threonine 114 hydrogen bond in yellow. And of course, serine 90 comes up as a hydrogen bond. There's another, looks like a pi-pi interaction with phenylalanine 94. It looks like there's also like one compound that has a pi interaction with histidine 95 up here. There is phenylalanine 281, which would give good interactions, and serine 285 would be the last residue that would give good interactions. So basically, if we wanted to build a really high affinity ligand, we'd want to build one that has those characteristics. I'm not actually familiar with how to actually do this sort of thing, particularly. So if anybody knows, I'd love to learn how to actually build one of these Pharmacophore models and build a ligand based on those interactions. Because the hard part is you also have to think about how you build your ligand in a three-dimensional way that it would satisfy all those criteria. And that's kind of what I'd be interested in actually figuring out how to do. I'm sure there's a way in Maestro. This is a very extensive program. I don't know how to use all the tools in here. So back to what we were talking about. Okay, so we basically docked 100,000 compounds using HTVS, high-throughput virtual screening. HTVS usually takes about 1 second per molecule, so my computer probably a little bit faster, but pretty decent computer setup here. So it's actually not too bad to dock 100,000 ligands. I've docked a lot more. So basically what we want to do now is go to our next highest stage of docking, which is going to computationally take a little bit more time. The next highest form of docking is called glide standard precision. Glide standard precision, instead of taking 1 second per molecule like HTVS does, it takes 10 seconds per molecule. So 10 times the amount of time for a bit better results. So here's what we're going to do. We're going to find the co-crystallized ligands. Actually, what we want to do is any compound that's not better than Win, our control, we're going to actually just delete from the work. Sorry, I didn't have that in the workspace. So basically now what we're going to do is scroll down to entry. I think it's 5,267, which is our control. Yeah, there it is. Okay. 5,267. Basically, the idea is any compound that didn't give us a glide score from HTVS that's not better than our control compound Win, we're going to delete it out. So we're going to, you click below the entry, we scroll all the way down to the bottom of the workspace, and some of these compounds, -6, -5, -4, basically a more positive, we're going more positive now. More positive glide score means the compound did not dock. It gets worse and worse and worse. And yes, there are cases where you have glide scores that are positive, which would be absolutely atrocious at binding. You hold shift, click. That should select all of the entries. This will take a little bit of time. I'll probably cut out some of this. This will take some time to select. Oh, that wasn't too bad. So that selected all of our 94,000 entries that we want to delete out. Because we're only keeping about 5,000, right? Yeah, we're only keeping those 5,000. Right click, delete. Delete all the entries, press OK. That might take a little bit of time. I basically always have my computer on and always running various jobs for different projects, so my computer does tend to be a little bit laggy, I'd say, overall. So basically now we have all of our 5,000 compounds that we're going to go to our next stage of screening. I'm going to double click to get rid of the receptor for now. I'm going to pull this back, and now what we want to do is just display the ligands. I'll do this all over here actually so you guys can see what the heck I'm doing. Okay, so from our HTVS, we're going to select all of our compounds. We could just hit that. That's all in one group, so that'll be the most efficient way to do this. And we're also still going to keep our co-crystallized ligand. Okay. Get rid of the receptor. There's a receptor down here, I can tell. Control. Okay. I think we're good. Just always like to double, triple check. Make sure everything's good. Make sure I've done everything correctly. Cool. So now we're going to pull this back to my other monitor. You can't see it now, but they're all selected. I'm going to go to ligand docking. Okay, ligand docking glide. We're going to use the exact same receptor grid file that we generated before, which was, we called it CB2 grid, and we generated that yesterday on January 30th. I'm going to leave this the same. Use ligands from project table selection, 5,252 ligands. Settings, we're going to use standard precision. So HTVS takes about a second per molecule. Standard precision takes about 10 seconds per molecule. And then eventually we'll use XP, which takes like 2 to 3 minutes per molecule. Okay, we're gonna keep everything. We're gonna keep everything standard. We're not gonna change any. Just use the default. What the job is. We're gonna call this glide standard precision SP, and then we're gonna call this CB2, and then we'll put the date. This is January 31st for me, 2022, and we're gonna hit run. Make sure everything's good. Yep, everything looks good. For reference, if we want to do a little bit of math on this, let's see. Calculator. We have 5,252 molecules times 10 seconds per ligand. That gives us the amount of seconds. To get seconds to minutes, we can divide that by 60. That's how many minutes. If we want to get it to hours, we divide that by 60. And we get about 14 and a half hours. I know my computer can do this a bit faster. I do have a decently souped up computer. And that's basically it for today's video. You know, we have the job running. That'll, I'll touch base with you guys tomorrow when that finishes. We'll talk about what to do next. I also have the other tranches all running in one file. This is gonna take a while to run. This is 500. I already filtered. I did the filtering that we talked about yesterday using QikProp, and there were 500,000 molecules, and I put them all into one file, and I'm running all the HTVS for these. That'll take like at least another whole 24 hours, maybe 35 hours to run all that. And I'll touch base with you guys when this glide SP job finishes, and then we'll talk about what to do from here. But we're getting there. You can see that this process is like it's like a funnel, right? It's like you have like a large funnel, right? And you dump a bunch of stuff in it, and only the best stuff gets to the bottom, right? When you filter something, the top of the funnel would represent like most of the junk that gets thrown away in the little tube, but the bottom would represent all the good stuff that comes out of that funnel when we filter these molecules. Till next time, I hope you guys learned a bit from this video, and I think the cool takeaway from this video is think about that idea that I talked about Pharmacophore modeling, where I looked at about 100 of the best docking ligands and what types of interactions are favorable towards the cannabinoid type 2 receptor. That's something that's really, it's good theoretical knowledge to have when you're thinking about designing drugs. See you guys probably tomorrow. Bye.